All right. Welcome everybody to another Calcaholic video. It's me, Andrew, and today we're going to be doing the Dirichlet integral, which is the integral of the sinc function over the reals. Now, the reason why I want to do this integral in the first place is because this specific integral comes up so often in other versions of the Dirichlet integral that I just want to have this as reference so that anytime I say that, yeah, this integral is what it is, I don't have to do the computation in the video, making it longer, because it is rather famous. So yeah, that's the purpose. I kind of want to plug myself in future videos if I ever do use this Dirichlet integral. So firstly, I want us to make the observation that if we plug in negative x here, our function does not change. So this is indeed an even function, so it can be rewritten as the integral from 2, or 2 times the integral, going from 0 to positive infinity of the same integrand. Cool, so we're just switching the bounds, right, using that property. Now, keeping that in mind, let's go ahead and introduce a parameter. So I'll say, suppose that this parameterization I of t is now equal to our integral going from 0 to infinity of sine x over x. And now what parameter am I going to introduce? Well, I want something that converges, which is going to be e to the negative tx dx. Now, why did I choose this parameter? Like I said, I wanted to converge, and I also need 2 points for t that are known values that I can use as kind of initial conditions to solve the integral in the future. So if I plug in 0 for t here, I of t equals 0, we'll see that we have, and I'll say that this expression is equal to I, which is the target integral. So I of t equals 0 is just going to be I, so that's the target integral. And then as t gets arbitrarily large, close to infinity, we go to 0. So we know 2 points here, which also relate back to our target integral. So that's generally going to be a good parameterization here, and that's why we choose that. Also, we want it to converge, and that's why we put the negative sign there, so that at infinity we are converging. If there was, opposed to if it was a positive in the exponent, then we'd be growing exponentially. So that's what the negative sign is for, so that we converge at infinity. So now what do we do? Well, Leibniz integral rule tells us that if we differentiate the left and right hand side, we get this derivative with respect to t of the integral that we had earlier. Now, let's observe our bounds, our limits of integration here, and notice that we converge absolutely, right? And our bounds are independent of the variable t, so we can go ahead and bring this total derivative under the integral as a partial. So we'll see that I prime of t now is equal to the integral from 0 to infinity of the partial of, with respect to t, of sine x over x e to the negative tx dx. All right, cool. So now notice this term here with the sinc function, this factor I should say, is completely independent of t, so it's just a constant multiple with respect to t. Now over here, this e to the negative tx, all that's going to do when I differentiate with respect to t is introduce a factor of negative x, which is going to cancel nicely with this denominator here. So let's go ahead and do that. We'll see I prime of t is now the integral from 0 to infinity of sine of x, I should say negative e to the negative tx dx. Now this probably looks very familiar if you're at least halfway through your BC or Calc 2 course. This is a integration by parts problem. But before I do that, I'm just going to absorb that negative sign so it doesn't bother me in the future, because I suck at remembering to keep those multiples in my final answer. So I'll absorb that and kind of switch my bounds now. So now I'm ready for some integration by parts, or more specifically, what I'm going to do is tabular integration, which is just a fancy name for integration by parts when you set up this table that I'm going to set up in a second. All right. di. We need to choose a factor in the integrand that I'm going to differentiate, which is, I'd say sine is pretty easily differentiable. And then e to the negative tx is easily integrable. All right. Probably need 3 here to get back to sine. So when I differentiate this sine, I will get a cosine. And when I differentiate this cosine, I'll get a negative sine. All right, now what about integrating here? Well, integrating this, I'll get negative e to the negative tx over, I was going to write x, no, it's t. And then integrating this again, I'm going to get e to the negative tx over t squared. Okay, cool. Now what do? Well, I multiply this guy with this guy, multiply this guy with this guy, and then I subtract this integral right here. So let's go ahead and do that. So now if this tabular is correct, then we should get this implication right here, that I prime of t, yes, I prime of t is now equal to this sine x. Now I notice there's an e and a negative tx as a factor, and what's left here is the sine x over t plus a cosine x over t squared. Okay, cool. Now what are my bounds here? I'm being evaluated over x equals 0. Sorry, I swapped those earlier. X equals infinity and x equals 0. All right, cool. So now what do I have left? Well, I have minus the integral of infinity to 0 of 1 over t squared will bring out. And what's left is sine x times e to the negative tx dx. Now notice this term right here is identical to what we had earlier as I prime of t. So I'm just going to erase it, save myself the time, just erase that and write I prime of t. Cool. So now what will I do? Well, I'll add this I prime of t right over here to the left and right hand side of my equation. So what that will do is make 1 plus t squared, oops. What that will do is make 1 plus t squared over t squared I prime of t equals this over here. So let's go ahead and evaluate this. At 0, what do we have? We have, let me get a color here. This goes to -1. At 0, this goes to 0, and this goes to 1 over t squared. So in all, we should have a -1 over t squared. Now I'm not going to bother with the infinity because at infinity, this exponential decay overtakes any periodic function, especially ones that are bounded between -1 and +1, like the trigonometric functions. So yeah, we're just going to look at this infinity. This exponential overtakes that and goes to 0. So we get -1 over t squared plus 0. And notice that we have a t squared and t squared over here, which we can multiply on left hand and right hand sides, giving us the following here. I'll write it on the new page. 1 plus t squared over t squared I prime of t equals -1 over t squared. So yes, these 1 over t squareds will cancel, and I prime of t is now equal to 1 over, I should say -1, 1 plus t squared. Okay, cool. Now, remember earlier about me saying that I introduced this parameter for a very specific reason. The reason being I know 2 points. And what was it? Well, it was 0 and infinity. So what I'll do is kind of space this out and integrate my left hand and right hand side from 0 to infinity. And I'll do the same here. Need to make this an integral with respect to t. And 0 and infinity and dt. Okay, cool. What do I have here? I have, by fundamental theorem of calculus, I have I of t getting arbitrarily large minus I of t equals 0. Now this is going to equal negative arctan of t getting arbitrarily close to infinity plus 0 because the inverse tangent of 0 is 0. So that's good. Now, what did we say earlier? Well, I of t with input arbitrarily large is 0. And this was the target integral. T equals 0 was the target integral. Let me verify. Technically, it's a half of the target integral. So we'll say I over 2. And now this is equal to negative sign. And arctan as t approaches infinity is pi over 2. So this means I over 2 equals pi over 2. And by observation, or multiplying both left and right hand side by 2, we get I equals pi. Awesome. So what conclusion can we make? Well, we can say, therefore, the integral from negative infinity to infinity of sine x over x dx equals beautiful pi. Now, like again, I wanted to say earlier, I'm doing this for reference for other videos that I'll probably make in the future where I'm going to be using this Dirichlet integral. So if you're here from one of those videos, then yeah, that's how you get this equal to pi. All right. Thank you for watching. Everyone have a great day. I'll see you in the next video.